Okay, this is lesson 4.2, exponent rules, including negative exponents. Now I know this is lesson 4.2, but this is actually the first lesson of Unit 4 in exponential functions. In this lesson, we're going to review 8 exponent laws, and we're going to apply them first once at a time, and then all together. So let's get started here. Our first 2 exponent rules are the exponent law for multiplication and the exponent law for division. The exponent law for multiplication says that when you're multiplying 2 powers that have a common base, you'll see a common thread amongst most of the exponent rules is that you're applying them when you're working with a common base. So we've got a to the exponent m and a to the exponent n, and since we're multiplying, the rule says to add the exponents. So we'd come up with a to the exponent m plus n. If we're dividing, we would subtract the exponents, kind of in the same fashion. Again, common base. A is our base for both. Power law is what happens when you have a power raised to an exponent. When that's the case, you multiply the exponents. Power of a product is if you have a multiplication inside a bracket and you have an exponent outside, the exponent gets applied to both of the bases, and then you would multiply. Alternatively, if you knew the numbers, you could multiply and then raise them to the exponent, but you'd get the same result. Power of a quotient law is that if you have a quotient, so a divided by b, and you had an exponent on the outside, again, both of the bases would get the exponent, and then you could divide. Zero exponent, if you have a base raised to the exponent 0, the answer will always be 1. Okay, and those are some exponent laws that you definitely would have seen last year in grade 10, along with these negative exponent rules, but these ones might be tougher to recall. If you have a base raised to a negative exponent, the way you can rewrite this is 1 over that same base, but with the positive exponent. The reason we do this is because when we're simplifying powers, it's simpler to write it with a positive exponent. Even though this looks more complicated, you don't have to work with a negative exponent, which is more advantageous right now. Finally, if you have a quotient and it's raised to a negative exponent, you would flip the base, and both bases get the exponent. It's basically the exact same as the negative exponent rule, because in this case, the base would be a over 1, so we flipped it, made it 1 over a, and both would get the exponent. 1 would get an n and a would get an n, but 1 raised to any exponent is still 1. So that's why it just looks like 1 over a to the exponent n. This one, both get the negative exponent, like the power of a quotient, and then to make them positive, you would do 1 over. Well, 1 over a to the exponent n would bring the a to the exponent n to the bottom, and 1 over b, when it's on the denominator, would flip it to the top. But what's easiest to remember is probably just flip the base, change the sign. Flip the base, change the sign. All right, let's see these rules in action. I've got 8. Convenient. We're going to simplify each expression to a single power, and you can do that if you're working with numbers or letters, but as soon as you start working with multiple letters, like this example, we're not going to be able to get a single power, like something in terms of a, b. We're going to get something in terms of a and something in terms of b. So I guess to clarify, a single power for each variable, if there's variables. All right, first example. We've got 3 to the exponent 2 times 3 to the exponent 4. And what you might notice is you have a common base of 3. When you have a common base and you're multiplying, you would add the exponents. And I'm going to show the adding step. You do not have to show the adding step. If you see this, you can go right to the answer, 3 to the exponent 6. Now, 3 to the exponent 6 is something you could evaluate, but the instructions say simplify. Simplify just means single power. We don't need an answer. An answer is not more simple. If it said simplify to a single expression, or simplify each expression to a single power and evaluate, then you would need a number answer. We don't have that. So just simplify to a single power. Second example, 6 to the exponent 5 divided by 6 to the exponent 2. We would subtract the exponents because we're dividing. 5 minus 2 is 3. Okay, multiplication and division laws, I think, are pretty straightforward. Power of a power. So we've got a power, 2 to the exponent 2, raised to an exponent. And when you raise a power to an exponent, you multiply the exponents. So we would get 5 to the exponent 2 times 3, which is 5 to the exponent 6. All right, next one's power of a product. We've got 5 times 2 to the exponent 3. And we could simply do 5 times 2, get 10, and make it 10 to the exponent 3. And that would be a single power. But alternatively, we could use the power of a product law that says distribute the exponent to both of the bases. And we would get 5 to the exponent 3 times 2 to the exponent 3. And now why would we ever do that? Well, in this situation, we probably wouldn't. We'd get 10 and raise to the exponent 3. But if one of these was a variable, like say 2 times a, or maybe a times b, if you had variables involved, the only way to simplify this would be to distribute the exponent to both terms. And we can't get closer to a single power here because we have 2 separate powers. So that technically would be our answer. If the bases were the same, we could add the exponents, but they're not, so we have to keep them separate. If it said evaluate, we could figure out what the answer is, but it doesn't say evaluate, it just says simplify each expression. It probably shouldn't say to a single power now that I think about it. It should just say simplify each expression. But if we're working with that description of a single power, we can't go any further, so we have a single power, 5 to the exponent 3, and a single power, 2 to the exponent 3. And that's as simple as we can make this one. E has 2 over 5 to the exponent 3. Now, what we would do is we distribute that 3 to both. 2 to the exponent 3 over 5 to the exponent 3. And again, if these bases were the same, we could subtract the exponents, but they're not, so we have to stop here and we have to leave it at this stage. If it said evaluate, we could do 2 to the exponent 3, get a number, 5 to the exponent 3, get a number, and then simplify the fraction. But again, it doesn't say evaluate, it just says simplify. F set up like a division statement, so we could use our exponent law of division, which would say subtract the exponents. Why I've included this example is because we have a negative on the bottom. Watch what happens. X to the exponent 5 subtract negative 3. Subtracting because we're dividing. Subtracting a negative is like adding. So we get x to the exponent 8. And there we have one fully simplified. Negative 6 x to the exponent 0. Now, this does not say negative 6x to the exponent 0. These are not the same thing. The only thing that has the exponent 0 is the x. So our answer is negative 6, and when you have something raised to the exponent 0, something raised to the exponent 0, the answer is 1. So that x to the exponent 0 part, this part, that's the part that's 1. So we get negative 6 times 1. And we can simplify that to just negative 6. And now it looks like we've evaluated here, but we've actually simplified the power, and we ended up with 1, and now we're just simplifying the number. So the answer is a single number. And H. H has got a lot going on here. Let's see what we can do. So we've got A's and B's on top, and we've got A's and B's on the bottom. Well, we can simplify the top and the bottom and then see if we can simplify it together. So I'm going to work on the top first here. We've got a to the exponent 7 to the exponent 2. Power of a power tells us to multiply. So we get a to the exponent 14. If we do the same thing with our b's, 8 times negative 1, we get b to the exponent negative 8. And I'm going to leave the bottom the way it is right now. And now we have division. So we could subtract our exponents. Now we can't mix and match here. We can simplify the a's separate from the b's. And since we're multiplying on top, we're going to be multiplying in our answer. So here's how this would look. We would do a to the exponent 14, subtract a to the exponent 3. Maybe I'll write that. A to the exponent 14, subtract negative 3, times, we got b, that's negative 8, subtract negative 10. And if we do some subtracting, we come up with a to the exponent 17, b to the exponent 2. And that's our final answer, positive exponents only. All right, let's flip it over and try some more exponent rules. A, B, and C. Simplify, express answers with positive exponents. That's a much better instruction. All right. So what we have here is a bracket times a bracket. So everything in this bracket is multiplying everything in this bracket. Well, there's only one term in each. So we're just multiplying the two terms together. Now to do that, there's 3 parts to each term. There's a coefficient, there's an A variable, and there's a B variable. So we're going to do each step separately. And we got 3 times negative 2 would be our first step, which would make us negative 6. A squared times A cubed would be adding exponents, 2 plus 3. And B, the exponent on B is just 1. The exponent's not written, the exponent's 1. And over here it's 2, so we've got 1 plus 2. Go add my exponents, I've got negative 6, A 5, B 3. All positive exponents. Negative 6 is a negative number, but it's not an exponent, so we don't have to worry about that. It's just a coefficient. Let's try B. B's got a single term raised to the exponent 3. Now, just like on the first page, power of a product, we have 3 things being multiplied here. Negative 4, p cubed, and q squared. Each term gets the exponent. The number gets the exponent, the p term gets the exponent, and the q gets the exponent. Here's how this would look. Negative 4 gets the exponent. P term, P3, gets the exponent. When you have an exponent on an exponent, it's multiply. And the Q term gets the exponent. So coefficient gets the exponent. P gets the exponent by multiplication. Q gets the exponent by multiplication. Let's simplify a little bit more. Negative 4 cubed. I'm going to do that. Negative 4, 16. Times another negative 4 would be negative 64. So I'm going to turn this number into a coefficient, and I'll leave my variables with exponents because we can't simplify that anymore. P9, Q6. And our last example. Here we've got 6 times x5 times y cubed divided by 8y4. We could simplify inside first and then apply the exponent, or we could apply the exponent then simplify. And either way is fine. I'm going to apply the exponent. So squared to 6 is 6 squared. Squaring x to the exponent 5 would give us x to the exponent 5 times 2. I'm not going to show the multiplication this time. I'm just going to go right to the answer, 10. Y cubed squared would be y6 over 8 squared and y4 squared, which would be y8. And now do a little bit more here. We end up with 6 squared is 36. X10, Y6 over 64, Y8. Now we can do a little bit here. We can try to divide the numbers, but we end up with a decimal. So we can just reduce it as a fraction. And we can divide top and bottom by 4, and we end up with 9 over 16. There's only one x term, x10, and the y's we would subtract. 6 minus 8 is negative 2. Now we don't want negative exponents in our answer. The only negative exponent is that y. So what do we do to remove the negative exponent? We flip it and make it 1 over y squared. So that 1 would end up in the top, 1 times 9 is 9, and the y squared would end up in the bottom. Alternatively, if we go over here, another way to come up with that answer is simplify the exponent, or simplify the coefficient, same way. X10 stays. And now since the bigger exponent's on the bottom, when you do your subtraction from the bottom up and put your answer on the bottom. If you do your subtraction from the top down, you put your answer on the top. Why this helps is, what's 8 minus 6? Well, it's 2. Since we went bottom up, put our answer on the bottom, y squared. We end up with the exact same answer, but in one step instead of doing the negative exponent step. So up to you which way you want to do it. I would suggest doing the subtraction bottom up if the exponent on the bottom is bigger. Make sure you put that answer on the bottom though when you do your subtraction. All right. 2 more, actually 1 more. I'm going to get you to try the second one on your own. This time we're asked to evaluate. If you're asked to evaluate and you have complicated exponents, you should use the exponent laws to simplify the expression fully first, then substitute. So that's what we're going to do. We're going to look at the first one here. We've got x squared to the exponent n. So we would multiply the exponents and we would get x 2 times n is 2n. Our y term is just y to the negative 2n. Not much going on there. And our x term is x to the exponent negative n. Now, we've got 2 terms with an x in it. When you have 2 terms that have the same base, you can use exponent rules. We've got multiply and multiply. So the rule of multiplication is to add the exponents. So we would get x to the exponent 2n plus negative n. And the y term would stay as just negative 2n. 2n minus n is just n. So we get x to the exponent n, y to the exponent negative 2n. Now we don't want to work with negative exponents, negative 2n. So we bring it and turn it into 1 over y to the exponent 2n. And now we have a term multiplied by a fraction. You would write it over 1, multiply across the top, x to the n, over, multiply across the bottom, y to the exponent 2n. So that's fully simplified, and now we would make our substitution. 2 for x, 1 for y, negative 1 for n. So let's try that. 2 for x, negative 1 for n, 1 for y, and negative 1 for n. Now let's see if we can evaluate here. 2 to the exponent negative 1, we'll leave that for a second, divided by 1 to the exponent negative 2, if we multiply. Well, 1 to the exponent anything is just 1. So we end up with 2 to the exponent negative 1 over 1. Take a little bit of room here. Which is just 2 to the exponent negative 1. And 2 to the exponent negative 1 expressed as a positive power. We would take the base, flip it, and change the sign to positive 1, which is just 1 over 2 to the exponent 1 is 2. So that whole thing simplifies down to a half. And there's one more example here, example B. I am going to get you to try B on your own. What I will tell you is the answer is 1, where should I write it? I'll write it right here and spoil it for you. 1 over 2 to the exponent 6. So you can try to come up with that answer on your own. Try to simplify the exponents first, then substitute and see if you can come up with that as your answer. Thanks for watching, and I'll see you next time.